Hello and welcome everybody to this month's Department of Energy Python Exchange. My name is Cameron Riddell and I will be your host this evening, afternoon, or morning depending on the time zone that you live in. As you all may know, our goal here is to have Python thrive within the National Lab System and associated research sites. In support of that goal, we are joined today by guest panelist Jan Janssen from the Los Alamos National Lab, who will be sharing his thoughts on developing a tool called pyiron, an interactive development environment that aims to simplify the lives of material scientists who rely on high-performance computing for their simulations. But before we get to the agenda and everything that we have laid out for today, I want to take a moment and introduce our panelists and remind everyone about a few key points about these exchanges. As a reminder, this call will be recorded, edited, and posted online. As a consequence, please be conscious of the information and the questions that you may ask to ensure that you're not accidentally sharing any information that's privileged or requires any form of clearance. Additionally, as you all know, we are a growing community, and we would like to stay in touch with each and every one of you. If you would like to be kept up to date with our monthly exchanges, please sign up for our mailing list, which you can find on the website meetup.doepy.org. You can additionally find recordings of all past exchanges on this site, as well as a recording of today's exchange once it has been edited. For next month's exchange, I just want to get this in here before we get started. Next month's exchange, we're joined by Max Grover and Zach Sherman from the PyArt project. This will be an absolutely fantastic exchange that I'm very excited for. But I do not want to overshadow this month's exchange. For those of you who have never joined us for a DOE Python exchange, I want to share with you that these exchanges are typically broken down into about 4 parts. First, we'll introduce our fantastic lineup of hosts and guest panelists so that you may all get to know them, as well as their respective fields and backgrounds. Then we'll kick off into a coding activity where we'll ask some very applied questions to our panelists to elicit some practical discussion about what best practices are in software development, and if I'm not a software developer, why do I care about coding? Thirdly, we will turn things over to our guest panelist, Jan, who has prepared some remarks about pyiron, Python, and reproducibility in the material sciences. And finally, we will wrap up with our full-blown discussion about points brought from our guest panelists about from our host panelists about our guest panelists' prepared remarks. And for everyone joining us in the audience, this is your chance to ask questions and engage with our panel to help us fully understand where Python fits into the life of a scientific researcher. So make sure you use that Q&A widget that's on the side of your screen, or if you're in the native app, should be on the bottom hand side of your screen. And enter your questions in there as they come up, and our panelists will field them either with you directly through chat, or we will bring them up at the live discussion at the end that I just mentioned. With all of that being said, I would love to go ahead and introduce our host and guest panelists today. For each of these introductions, I'll share the name and affiliation, and our panelists will tell you about what type of questions they're here to answer, which is really just code for what are they an expert in. As I mentioned, please, if you're curious about who any of us are, you can find all this information as well as past recordings of our past exchanges on meetup.doepy.org. Our host panelists today, I'll start with myself. Hello, everyone. My name is Cameron Riddell. I work at Don't Use This Code, who provides training and consulting for Python and computer science-related programming. I am here to answer questions about anything related to Python in general, or about the specifics in its scientific stack. I especially love questions about NumPy, Pandas, and Matplotlib. Next up on our host panelists, we have James Powell. James is affiliated with NumFocus, and I'm curious, James, what types of questions are you here to answer for us?
One of my favorite types of questions to answer is, why do I care about something? I work with a lot of scientists, and they often see the extreme complexity that is required in order to deliver high-quality software, and they're not sure, well, what do I really care about coroutines? What do I really care about generators? What do I really care about pandas? I would love to answer for you why you might really care about some of this technical sophistication, how it'll affect you in your day-to-day life.
Fantastic. So when we need to answer, what does this all mean and why do I care? We'll definitely be coming to you. Next up on our host panelists, we have Matthew Carbone. Matthew works at Brookhaven National Lab. And Matthew, what types of questions are you here to answer for us today?
Can you hear me? Make sure my
Yes.
mic has been going in and out. All right, great. That's just my blue jeans problem. So yeah, I love answering questions. Well, my favorite types of questions are like, how can I speed up my numerical scientific computing in Python? How to avoid using for loops, stuff like this. But as a general summary, I specialize in machine learning for the physical sciences. I do some theoretical condensed matter. So anything surrounding how you do these numerical techniques in Python, I'm there for.
Perfect. So we'll definitely be asking you about questions about best practices when it comes to really crunching numbers in Python. Next up, we have Andy Barber, who is also joining us from the Brookhaven National Lab. Andy, what types of questions are you here to answer for us today?
So I use Python to analyze data and collect data, often with either mature or emerging libraries, and working with people that don't have a lot of Python experience. So I'm there to help ask questions about making your code more approachable, or for people getting started, how to get started.
Fantastic. I love having your background here with us because we have a lot of people who come from kind of a heavier software development background, and you are really key in helping to bridge the gap and answer those questions. Why does anyone care? If I just do research, why do I care about programming? Why do I care about coding? So I love your background. Love that you're here joining us today. Next up, we're also joined by Tanny Chavez from the Lawrence Berkeley National Lab. Tanny, what types of questions are you here to help us with today?
Hello. Since my background is in machine learning and image processing, I think that something that I would love to discuss more about is on how to make machine learning algorithms more approachable and accessible to a larger scientific community, so they can be helpful and used efficiently within this community. So those are the type of questions I'll be looking forward to discussing more about.
Perfect. So it sounds like you're here to just really help bridge our gap between what is the really computational side and what are those best practices and how can we relate those to people who are writing code every day. That's it for our host panelists. Our host panelists are all from the National Lab System, and so I'm very excited to have them joining us. Next up, our guest panelist is Jan Janssen. Jan Janssen is also from the National Lab System, specifically Los Alamos National Lab. And Jan, as I've mentioned, is working on a interactive development environment called pyiron. So Jan, what types of questions are you here to answer us, and what are you, just a little bit about, what are you here to share with us today?
Yeah, so I want to share about the pyiron framework, and the idea there is basically coupling simulation codes written in Fortran, C, other languages, ideally in a Jupyter notebook. So really abstract the technical complexity from the scientific workflow. Yeah, and I'm happy to share my work and present it here.
Fantastic. So Jan is here to share with us a lot today, and I'm very excited to hear what you have prepared for us. Lastly, I want to extend to everyone in the audience an opportunity to join us. You can become a host panelist. You can sit up here. You can field questions and help drive discussion for these monthly exchanges. If you want to become a host panelist, please reach out to us at doepy@dutc.io. And you'll also find that email on the Meetup website. That's meetup.doepy.org. With all of our introductions now out of the way, we can dive straight into our exciting coding challenge, which I believe James Powell has prepared for us. James, would you like to tell us a little bit about the coding challenge, and I'll bring it up for you?
Today's coding activity is called Don't Even Get Me Started. Here's the scenario. When you are talking to a scientist who has to write some code, there's all of these thoughts that they have in the back of their mind, all these worries they have, that they're worried, if I don't think about this before I even get started, my code is going to bite me in the butt. In 6 months' time, it's going to blow up in my face. And I think that this sometimes is a disservice to our scientific research staff, who oftentimes just don't have the bandwidth, don't have the ability to worry about all of these things. And so here's how the game is going to be played. We'll walk you through a couple of different scenarios, about 6 in total, plus 1 bonus, where we're going to set you up with somebody who comes to you and says, Matthew, this is what I'm trying to do. What do I need to worry about when I get started? But there is a special rule for this game. For everything you tell them, you got to worry about this before you get started. You must give them at least one, if not more, things that they don't have to worry about. Because our goal here isn't to pile more on their shoulders. Our goal here is to say, you know what? You don't have to worry about the domain name for the open source project that you're coming up with, but maybe you should worry about the project name because it could be potentially confused with another project or it could be hard to search for. You don't have to worry about the logo for your project. You can always come up with that later. So that's one thing to worry about and two things not to worry about. You are at net benefit. And so why don't we go to our very first scenario and open it up to our host and guest panelists. Here's the scenario. Scientist comes to you and they say, I have to develop some software. It is very critical. It is very complex. It's going to be under multiple frequent releases. I don't have a lot of resources to manually build this thing, to release it, to deploy it. What do I need to worry about before I even get started? I've heard about CI/CD. I've heard about Travis CI. I've heard about automated builds. I've heard about automated testing. What do I really need to worry about before I even get started?
I think I can probably go first. So in this case, probably something that does come to mind is probably that we need to do before setting anything up is basically line up all our expectations, our end goals, what is like the minimum product that we are trying to come up with. So for example, let's say that someone is trying to build a system that they would like to support several different types of data sets. How about before we start building the code itself and the architecture and trying to come up with all these creative ways to ingest all these different types of data, why don't we first say, okay, these are the types of data that we're going to support, and we start there so that we have like a clear idea of what are the things that we're going to start supporting, build up from there so that then we're going to start ingest new things. So that will be probably my first thought on like where to start and what to keep in mind. As to probably what to ignore, I will probably say just probably, and this goes like in line with what I just said about like keeping in mind, but just ignore all those other things that will not be supported at the very beginning. You know, just focus on something that is like very strong to start with, like something like, as I mentioned before, like the minimum product, and then we will start consider all the other things that we're not considering at this time.
Nobody else wants to go?
Maybe to follow up on this, I guess I would look at what is already available in the open source community, because depending on what's your challenge, you can maybe use dependencies. And then for the first start, I would just fix all the versions of my dependencies. So don't care about having support for the latest version of any software package, but just fix the environment and keep it fixed. That makes less to worry about one version is updated and maybe it's no longer compatible to another dependency of yours, and resolving all these dependencies. And just by keeping them fixed and help you to accelerate the development cycle. And then once you have the minimal product, then you can look into updating your dependencies and moving forward there as well.
So Jan, I have a follow-up question on that. Does that mean that if you are trying to build your software stack and there's one little dependency and you're kind of worried that somebody is going to abandon that, you're going to have to maintain it, just don't worry about it, get your code out there and then worry about that later? Or is that something that you worry about up front? Those dependencies
I guess
responsibility later.
The size of dependencies definitely, but what I see is that people say, okay, I just need NumPy, and now suddenly NumPy is progressing in the time I do my development, and some users use it with an old version, some users have a more recent version. I would say I only support a single version of NumPy when I start, and then I can maybe extend it if there are enough users who need a different version. I wouldn't go so far to say I pick a very specific library that maybe only a single person developed, and I would check that my dependencies are somewhat reliable or rather big in my field.
I have a question, and I want to open this up. What about things like versioning strategy? Personally, I think the actual strategy, like whether you use Semver or something like that, you can change it later. You don't have to worry about it up front. We've seen a lot of projects change from one style to another style, and that's fine. However, I think that maybe you should think about packaging a little bit up front. in part because I feel like you'll never get the critical base of users unless you make it easy to install. And it's not unusual for maybe you to discover that some particular packaging system that you wanted to support later has some limitation around what you're able to do, how you're able to provide, multiple different streams of the same package or whatnot. So I think maybe thinking a little bit about how you do the packaging up front is worthwhile.
Do you think just grabbing a cookie cutter repository that kind of has some Python packaging already built in for you might be a good place to start there?
I'll let Andy go because I have very controversial ideas about things like cookie cutter.
I think as a user of emerging kind of things, I think it's great if packaging can be achieved. But based on Jan's initial point, that really resonated with me. If it's up front and up clear on the GitHub page, what versions of NumPy and pandas and whatever else that are expected, then it's really easy for someone to set up an environment that meets those requirements, as long as the imports come from sort of standard Python libraries.
And then I'll give the final comment. I am very skeptical of starting with cookie cutter or these templates. And the reason for that is you never know what the defaults actually are. You never know whether those defaults will be compatible with something that you decide you want to do later. I understand that these conveniences are extremely attractive, and I understand the attraction of them, but just that feeling of what is there that I've already set up that's going to preclude me from doing something later, it always makes me a little bit nervous. But I think, Cameron, why don't we move on to our next category? This one maybe is a little bit easier. Here, you have a user, and they control some sort of instrument, and it's an important instrument. They're frequently updating their code. Maybe their instrument is frequently being updated. What do they need to worry about with regards to testing before they even get started, and what do they not need to worry about at all? And before Matthew jumps in and says, don't even bother testing until you already have something out there, that's probably an appropriate thing, but maybe we'll add a little bit of clarity, a little bit of nuance to those comments.
Was that your way of prompting me to say something?
Go ahead, Matthew.
I mean, I guess I can just state the obvious, which I don't have much expertise in using code to control real world things. I deal with mainly, as my wife jokes, I'm a fake scientist because I only work on the computer basically. So I would think right off the bat, you have to worry about two very important things. One is you want to minimize failure scenarios at all cost. Obviously, if this is a very expensive instrument, then you don't want to run any risk of your code really breaking it, right? And a sort of analog to this, I've done a little bit of, I know some people in the finance space who have a similar situation. Their code controls people's money, right? So it's a serious thing, right? You don't want to mess with it. So one thing they also have is a sandbox environment. So what you can do is you can build like a fake machine to test against, right? You want that sandbox to basically mimic, right, how the actual robot takes its inputs and how it would then provide feedback to your code. And then you can use that, right, as sort of a fake robot to test against. And then I have to provide something you don't have to worry about. I would say in this case, you want to minimize you shouldn't dedicate as many resources, I would suppose, to making sure everything is working perfectly before you make sure you minimize the catastrophic failure scenario. I don't remember if it's like minimize the maximum or maximize the minimum or something, but it's one of those. So.
Any last comments before we move on to the next category?
So I guess we also have this issue here, and particularly with hardware, we find that it's good to store all the outputs and the corresponding inputs, and then use those to build your test cases. Right. So because it takes so long until we get feedback again from the machine, I want to basically have a database of potential input that I gave to a machine, and then the resulting outputs to see that my code is still working with these parameters.
Fantastic. These are all great comments. Why don't we move on to the next scenario? Here, we're going to get a little bit more specific. You have a user who comes to you and they say, I need to build a GUI or a web app for my instrument. What do I even need to worry about before I get started? Do I need to worry about web versus native? Do I need to worry about React versus Vue? Do I need to worry about Chrome versus Firefox? What do I need to worry about before I even get started? Qt versus GTK?
So I guess for me, being in the Jupyter environment, I just use the Jupyter widgets, and then it's rather simple to build a simple website based on this, as long as it's only accessible internally.
What about Jupyter widgets versus Matplotlib widgets? Do you worry about that ahead of time?
I would see whichever example matches more closely what you try to achieve. And
Just
then
get it done and come back
get
to
it
it later.
done, because like if it's later on in an application that's used by many people, there's going to be someone who can bring it to the right format or to the more scalable one. But to get the first version out, I typically choose, okay, which example more closely resembles what I want to achieve, and then go with this one.
Yeah, I definitely would agree with Jan there. I think just trying to get something simple out that works should come a little bit before you really, try and support every single platform or every single backend available. Get it working on one, and if the project is a huge hit and you need to scale, then you can focus on scaling. But if you're focusing on scaling out the bat, and I don't think a lot of us are, familiar with every single type of backend or interface that's out there, I think you're just going to slow down the production of the actual core pieces of the code that you need and be wasting a lot of time on, oh, how do I get it to look pretty, right, in different browsers? Or how do I want a side-by-side native app as well as one that runs in the browser, because I'm a single person and I have the full development power of, some big name companies who do that. Gonna waste a lot of time.
I think there was one comment from Tanny, and then we'll.
Yep. My comment is more related as well to having testers or beta testers as soon as possible. Like, don't, worry too much about it being pretty or, being like flawless. Like, as soon as you have a working product, in any state that product might be, maybe, like the interface doesn't look as great, doesn't have yet the logos, just have someone going over the process. Because many things for us in particular as developers may seem very intuitive and very user-friendly, as we like to say. And at the end of the day, we realize as soon as someone else uses it that it was not user-friendly at all and a whole redesign is needed. So I will probably say get to testing as soon as possible and do not worry about minor details as to whether the header is correct or, like if I have all the logos in the correct place or things that are still moving a little. Have someone just going over the whole process, make sure that it's actually user-friendly before moving forward and keep developing the website.
I'll add one final comment and we'll move on to the next category. If you're building a web app, understand the strange paradox of the JavaScript ecosystem, namely that any code that you write today is likely to run for the next 20 years. It is extremely stable. JavaScript from websites 15 years ago still runs more or less as it did 15 years ago. But at the same time, your dependencies are at extreme churn. So a dependency that worked 6 months ago may not work anymore. Just the extremeness of the churn of these ecosystems, where from version to version in the span of less than a year, things will break. And so what that generally means is be a little bit more careful when you bring in external dependencies, and do worry about ahead of time what those dependencies might be when you're dealing with web apps, in part because they churn so fast and they break so much. But at the same time, don't worry about the overall longevity or the platform, because largely any JavaScript code that you're going to write today is going to still run more or less the same in 10 years if the browser's still around. Shall we move on to the next scenario? Here is a very hard question. Somebody comes to you and they say, I'm developing some research code. Maybe I'm putting out papers associated with this. My grant or my institution requires that the code will still run in 10 years' time. What do I need to worry about before I even get started? Do I need to worry about data formats for the data? Do I need to worry about what versions of the libraries I use? Do I need to worry about containerization? What do I need to worry about before I even get started? These are hard, aren't they?
Well, I actually think this question is hard because it's almost hard to answer, in the sense that it's hard to even like it's not like I don't have an answer, right? The answer to me is yes. You have to worry about. The answer to me is yes, right? Like everything you just said, right? But on the other hand, there's an unknown here, which is maybe just the future computers in 10 years like are chips in our brains and they don't run Python. Like, and then what are you going to do, right? So in a way, there's almost an unknown about the future. So I think if we're going to proceed under the assumption that the standard practices will be followed in 10 years, then it should just be as simple as worrying about, yes, do I need to, turn this into a Docker container, or do I need to just have a requirements.txt file, right? And I can install using pip, right? Probably any of these things is okay as long as it's complete for your system. Yeah, I mean, and those things all come prepackaged with the right versions and everything. So that I would think should be sufficient, especially for whatever research funding source you're worrying about.
Anything you don't have to worry about that you can worry about 5 years into the 10-year time frame?
Oh, geez. Do you not need to worry about? Yeah, don't worry about reproducibility in 100 years. Worry about what you can control, I would say, and don't worry about what you can't. So what you can't control is like, will future computers have support for Python? Like, whatever that means. In all seriousness, though, like actually, like don't worry about things you can't control, I would say.
I'm very curious to hear from Tanny or Andy. What about things like data formats? Do you worry about how you store your research data because it may not be a format that is widely supported in 10 years' time? Or is that something where you just figure, in 5 years' time, I'll just convert everything over?
I think for me, I don't really worry so much about the data format. I think where we most often get in trouble is using different systems currently, because the libraries, especially when you rely on random number generation to initialize something, different computers and operating systems have different ways of picking the first number. So I would say it's really important to specify the seed that you want to use to start a process. So that is what I would say you should worry about, and not worry about so much the data format, as long as it's a standard data format that's currently supported, because other developers will make sure that you can have backwards compatibility.
Do you worry about that the person who maintained this code retires 7 years into the 10-year time frame and nobody knows how to manage that code? Or is that something you just do? You manage it when it happens?
You manage when it happens, but you also try to pick code bases that have a wide community support.
And Tanny, do you have a comment on that before we move on?
Yeah, something very short as well, that, I completely agree with Andy. I think that, overall, I wouldn't worry that much about the data format. But, from a machine learning perspective, reproducibility, it's a big issue, and it's a very hot topic. And I mean, I have seen myself, like in different, not even just packages, but also programming languages, like, for example, MATLAB. The way the numbers, like the random numbers are generated, the way the seeds work, are a little bit different when it comes to different releases of MATLAB itself. So I would probably say, if someone were to given this prompt of like having reproducibility on a 10-year time frame, I would probably ask, what does reproducibility mean itself? In the sense that, so if someone were to tell me I want to get this exact same number under these experiment conditions, I'll probably say there's no way to do that, not even within the next probably 10 minutes. I will probably say, what is our bandwidth of error? So what's our margins? Like, what are, for example, the standard deviations that we can get with respect to our results? And what exactly is that margin of error with respect to that result? Is it just the lost plot function? Is it just the final result, the accuracy? So I think it really depends on what the target itself is. But yeah, those are the thoughts probably that come to mind as reading this prompt. And as someone in machine learning, I feel like reproducibility is such a topic and something kind of like complicated to target. Yeah, very, very interesting prompt though.
That is a fantastic response. But why don't we move on to our fifth category? I have to develop a library to support users at my own facility. what do I need to worry about before I get started? Do I need to worry about how I deploy this code to them? Do I need to worry about testing? Do I need to worry about the user experience, the UI of this code? Do I need to worry about what language I use, what version of the language that I use, what version of the dependencies I use? What do I need to worry about?
So maybe I'll start there because something that I have to do. I would say that you should refer to like the ongoing projects that you first have, and like let people that have already made decisions ahead of time and spent a lot of time thinking about those things. As long as there's a consensus or even like a standard for the facility, you should just choose those things so you don't have to spend time thinking about that. So that was this thing that I would not worry about at all, even to like where it should be and how it should be installed. Those things may already be known. I think what you need to worry about to support your users is how your users who may not be so Python savvy can get feedback to you so that you can correct bugs and add features quickly in a way that is inclusive so that you have a successful library.
You need to worry about how-tos and tutorials and that kind of documentation?
Yeah.
Is there any kind of documentation you don't have to worry about?
How to contribute and make crazy code, because maybe you're the only one that's doing it, but maybe a single developer thing. So examples. So I think, documentation is two flavors. It's for the people that use it, and then there are the people that develop and support the library. And I think oftentimes, too many projects have very overly technical details that are meant for developers that kind of scare new people away.
I'm very curious to hear from Jan. Does programming language choice come into this? Do we need to wring our hands about, oh, do this in Fortran? No, do this in Python. No, do this in Julia. Or is that something you just figure out as you go along?
So I get two things. With the programming language, I thought it was much more a question. I feel now the community, at least on our side, is very much focused on Python at the moment. So before we had Bash scripts coupling Mathematica codes, MATLAB codes, Fortran codes, and C++ codes. And now I can do 90% of this stuff already inside Python with the standard Python libraries. So in this way, I guess it's much more uniform. Looking at this question, I think I would first worry about the interface and try to make only as few as possible functions available to my users, which allows me to restructure the internal workings of my library several times. If the interface is not clearly defined and the user is thinking very deep into your library and say, oh, this function looks nice and that function looks nice, you might have a lot of trouble if you change something internally or update it, or just the import path changes because you do a refactoring of your library and users start to complain. So what we learned with the pyiron library over the recent years is really just to say, make the imports as simple as possible, provide them a very clear interface, and then you can have more flexibility to structure the internal workings of the library.
Fantastic. Why don't we move to our last category before our bonus round? Let's say you need to develop an open source library to support users throughout your field. I think Jan's answer for the previous one was fantastic. One thing and one angle that I'd love to hear about is, how do you learn how to say no to your open source users? How do you learn how to say, I'm not going to worry about that. Come back later if you want it, but this is just going to create too much headache today.
On that, I can just say, if someone's like, hey, I want this feature, do it yourself. That's the point, right? Like, don't ask me to do it. If you want it, you do it, right? No, in all seriousness, I'm actually dealing with, getting a package ready for release. It's a small package, and it's for writing spectroscopy input files. And I have collaborators, and some of them want to do a lot of stuff with this code. And I'm like, guys, listen, this is the scope for the first release. We will do the rest later. But if we keep adding stuff before we release, we're never going to get this thing open. I'm never going to get past legal, right? Like, let's just get this out there. Then we can worry about the next release. So I think the first thing I would worry about is, right, what is the scope of your release, of your first stable release, right? Your first stable API, V1, so to speak. Don't worry about every edge case, right? Don't worry about what your friend who has the most specific possible use case ever, right, wants you to do, right? develop for the 95% of people who will use your code, and then the 5% who want an edge case can do it themselves. Right? That's the beauty of open source.
For your upcoming release, do you worry about code quality? Are you worried about, oh, somebody's going to look at my open source code and it's not going to be very good quality and they're not going to use this? Or not? Do you worry about bugs, or do you just say release it to the world and figure out the bugs later?
Oh, no. I'm extremely crazy about this stuff. So, and actually we'll hopefully be submitting it to a journal that actually reviews the code. So yes, I'm extremely concerned and extremely attentive to documentation, both technical doc strings and tutorial examples and walkthroughs. And yes, absolutely, we're very concerned about bugs. I don't want to release a buggy code. I accept the fact that the code will have bugs, but I want to do everything in my power to make sure that it's stable enough for most people during release. So I think these are two things you definitely want to worry about.
What about abstract code quality? Like you could have solved it this way, but you just found the hacky solution. Do you worry about that, or do you figure you can always refactor later?
No, I also worry about that too. And one of the principles of, I think, an initial release is extendability. You want it to be very easy for people to come in and use, for example, an abstract base class, right, and build their own object. Understand the sort of design philosophy of the code, right? How did you build the core objects and the core functions in your code so that people can build on top of them, right, in a very modular way? I absolutely think that's something, again, for the prompt, right, you want to develop an open source library, right? If you just want to deliver a one and done, then you're finished, then fine, do whatever you want. But if you want to deliver an open source library, which almost by definition should have these qualities, you have to worry about extendability. You have to worry about the design abstraction philosophy, or whatever you want to call it.
Fantastic. Why don't we move on to our last and our final category? User comes to you, they say, my code needs to support increasingly large data sets, potentially beyond what can be handled on a single machine. What do I need to worry about before I even get started? Do I need to worry about Spark and Hadoop and DAS? Do I need to worry about my code being multi-threaded capable or multi-core? In our last session, we heard that this is one concern that at least the authors of tools like in the Iris HEP ecosystem were very concerned about upfront. But what would you say should be concerned about upfront?
I guess it always depends on where we are at the stage of the development. So if we already have users and they already get close to the limits, or we see, okay, maybe if they get a new experimental measurement device, they will definitely break the limits. Then we have to worry about things like data size. But if it's, again, the stage of, I want my first release out, I also fear that we have so many assumptions how people will use the code, so many nice ideas for features, and then there are some features which the community never picks up. So where I wrote a lot of documentation, and then suddenly somebody came up with a much simpler solution, and that grew like crazy. So I wouldn't overthink it as well.
Jan, similar to the question of how do you tell a user no, how do you tell a user this project isn't for you? It's not designed for your use case. Please don't use it.
I would be very open about competing solution. So I guess we were all on not on a green field. There are always other people maybe working in a similar field, trying something similar, and just list them at the end of your project page and say, okay, these are other parts, or they are also available. And for such a user, I would try to point them to one of those other solutions where I see maybe a better fit.
I'm very curious to hear from Andy or Tanny. Have you ever had this circumstance? The code now needs to support data, and you need to change fundamentally the way that it works because the data sizes are too large. Was that something that you need to worry about ahead of time? And what characteristics would you worry about ahead of time? Or do you just deal with it when it happens?
I would.
Go ahead, Tanny.
Okay, I would love to say that I consider it before implementing. Unfortunately, I did do it the other way around. I implemented something, then realized that it was not, it couldn't handle the amount of data that, of course, Beamland scientists handle, which was entirely my bad. Overall, I'm going to say that you always have to think about your target audience first. Like in this case, if you're developing something for someone in particular, and if their science, just the nature of it is just creating a lot, like a very big amount of data, you do have to take that into consideration before developing the code. So I'm going to say, for example, like if I were to go back, or from now on, what I will probably do is first, take a look at the resources I have. and probably set my boundaries towards those resources. So if I go, for example, and I'm going to start, for example, with like a single cluster with LBNL, I will take a look at what are the hardware requirements and what are the constraints that I have regarding those hardware constraints, I'm going to say, and trying to hit those first. So my first release will be focused on, for example, this machine, this cluster, either this server, and I'm going to say, okay, this is as far as I'm going to go for now until, for example, we can go to our next step, for example, something like NERSC that can handle a lot more data. So I think that that's probably what I will probably do differently. I'll just set my boundaries and my constraints according to the hardware that I have available and make sure that that can handle, we could say, like an average size data set that my target audience is trying to process within this cluster. Andy, you also had another comment.
Yeah, I think it was just along those similar lines. We have code that I guess some parts of it are easily parallelized with things like joblib, and other parts were not. And so, my experience, I guess, is having an existing library and figuring out how to make it work parallelized. So if you don't know anything about how to parallelize code, like you don't know what Dask means or OpenMP or any of these things, I would personally get started with something that's much more simple with a lot of documentation. But if you're a developer and you need to learn those things, then maybe it's the different way to do it. But for me, it's a little bit more comfortable to sort of benchmark things that I understand and then think about how to make more complicated code that is really meant for parallel resources.
Thank you so much for that, Andy, and thank you to all of our panelists for participating in this month's coding activity. Don't even get me started. We can see, and I've been keeping score in the background, that for the most part, we can maybe remove certain things that scientists feel like they have to worry about, but don't necessarily need to worry about up front. Unfortunately, keeping score, it does seem like we are in the net positive. There maybe are a couple more things to worry about than we might anticipate. But if you have any questions, follow-up questions on anything that our panelists said, you'd like to understand more about the sigh when Andy says, okay, we had to deal with the data set and it grew too large, or Tenny says, oh, I didn't quite design this, and to understand what they did in order to address these problems, please feel free to use that Q&A widget, but I'll hand it back over to Cameron to get us started with our main event. Cameron?
Fantastic. Thank you so much, James. That was an awesome game, and I think we conjured up some great responses and great discussion amongst our panelists. With our game now behind us, I would love to move in to Jan's prepared remarks. Jan is here to talk to us about pyiron and how it can help our everyday researchers. So with that being said, Jan, I will turn things over to you.
Okay, let me share my screen. Okay, now. The idea there is basically going from an atomistic simulation to really simulating full material properties. And here I just show a finite element model of a car. And that should all be done in like a single framework. This is work that I started during my PhD back in Germany at the Max Planck Institute. And now I'm at Los Alamos, where we in particular look at how can we scale up these workflows to run on the large supercomputers. Okay. Why do we care about material science? And I just want to give like one example here, that's the development of fusion reactors. And so you see here a picture of the upcoming ITER reactor. In this building, you will find the tunnel where the fusion is then happening in. And you can already see that designing these parts and like developing the materials which can withstand this high amount of heat, you don't want to do this just in experiments, right? So you want to really be able to simulate these parts, what materials are required, design them on the computer, and then only implement them once rather than testing many different materials until you find the one that is suitable for a fusion reactor. And so we are now really at the stage where we want to use simulation to predict the materials of the future. To do so, there are many different aspects that we have to cover. So here again I have my material sample. We can look at surface effects, corrosion being one of the more popular ones. We can have chemical effects, electronic effects, vibrational ones, so that is when my atoms are moving. And then definitely also the coupling of all those, right? So if the different effects couple with each other, it makes it much more complex to simulate all this. And then there are macroscopic effects, like, for example, considering the grain boundaries, the grain orientation, dislocations, and so on. So what this highlights is really that material science in itself is a rather multi-physics approach, right? So we couple simulation code, and that's really also the big challenge there. Coupling codes developed in different communities, from chemistry over physics to material science. They might use different units, different input files, and so on. And that's really the challenge. And many of these codes were really written in Fortran or C++ and are don't yet have a Python bindings or easy ways to interface with them. So why is this interesting? And then just to give you one highlight of our research, I show you the heat capacity for calcium. There are experimental results as the black symbols, and then two theoretical predictions as the blue and the orange line. And you see they really nicely lie on top of each other. And to understand the importance here, the only information that we provide there is the interaction between the electrons. Based on this, we can then simulate full elements and really the heat capacity of bulk samples, and have really not only a qualitative but really quantitative agreement with the experimental results. And that's very important because we could say, okay, the experiment already gave us the numbers, yes, but in particular here for the BCC phase, the larger scale databases previously trusted this upper branch here. And only with our theoretical predictions, we were able to convince them to then also follow this lower branch. So we're now really at the stage where we can validate experimental measurements with theoretical predictions, which only include the interaction of the electrons. And so that's really what we call ab initio, so basically from the start, doing the thermodynamics and really achieving quantitative predictions of material properties. And let me just very briefly explain how we get there. So what we use is an adiabatic approach, where we calculate the free energy based on different contributions. So one would be our total energy volume curve. And you can imagine this, I just take my sample and I compress it. And so I can see a response, and there's a certain equilibrium lattice constant. Then I consider effects of the electronic temperatures, the phonons, so those are the vibrations of my atoms in the crystal lattice, and then further anharmonic effects, which typically we would calculate with thermodynamic integration. When I look at this in terms of like the different simulation codes, the first two properties, those are more or less standard properties, and they are available in standard DFT codes. So one example here being the VASP DFT code. Already for the third one, so the phonons, you typically would use a specialized package to set up all these calculations and then run them. And when we come to the thermodynamic integration, so basically what we do there is coupling two simulation codes. During the runtime, we fit an intermediate potential and do then the integration. So that really requires a combination of different simulation codes. And that's really the challenge there. We are able to really achieve this quantitative predictions from ab initio thermodynamics, but it requires us or it typically results in rather complex simulation protocols. And that's the kind of challenge we wanted to address with the development of the pyiron framework, right? So combining different codes, which might internally use different units, which are typically written in Fortran, C++, or other languages, and make them all accessible with one user interface as simple as possible for our users to really focus on the scientific part. So we took one step back and thought about, okay, how would our simulation look in like an abstract way? Right, so I have my idea. I would say I have a model, and then to validate this model, I have a very specific idea. Okay, I say I do this specific test. So that's what we call a project. And in this project, you would write the input, in our case, in the Python programming language, and we call this the generic input. Then the framework takes over. So all the parts here in the gray box, they are all automated. Right, so the framework translates your generic input to the code-specific input files. These can have like weird formats. Many of them are still text file based, and so on. We would then execute our simulation code. So that would be like for either on your local computer, but in many cases also submitting it to a supercomputer, submitting it there to the queuing system, waiting until you get your allocation time, and so on, until you get the output files, and then afterwards we get again the output files and convert them to our generic format. By using the generic input and generic output, we can apply various kinds of analysis to multiple simulation codes. So I only implement the analysis once and then apply it, basically reuse it for all the different codes. So in this case, it would be for my density function theory code, there would be the electronic convergence. I maybe want to collect data for multiple calculations, analyze this data, and finally, so that would be fitting my energy volume curve and then finally visualizing it. And that's the stage where the user takes over again. So the user validates this result, see, okay, does it confirm my model, or maybe I have to update my model and do another iteration of the simulation lifecycle. So by covering the whole lifecycle, pyiron is really able to capture the whole provenance. So I really have the dependency of the different objects, and with this can really reproduce the whole workflow and the thought process during the development. Based on this, also the most central objects, so we use the pyiron objects here, are typically connected to 3 parts. So one is being the Python user interface, and I will show this in more detail in the following slides. The idea there is we use Python as programming language, a lot of operator overloading, but also factoring to combine these objects. The pyiron objects are then connected to resources. So this could be the specialized code. So for example, my simulation codes, the computer clusters, so the submission to the queuing system, the transfer of the data there, or parameter databases that are available. And also the objects are connected to the data storage. So here we use the HDF5 format. So it's a hierarchical data format to store our data. We have an SQL table in addition to track the dependency of multiple objects. And that basically allows us to serialize our objects and transfer them between the different computing systems. So the aim here is really for the scientists to abstract the technical implementation away from the scientific simulation protocol. So how does it look like as a scientist using the software? The scientist will use it just from a Jupyter Notebook or Jupyter App environment here. As you can visualize the atomistic structure that you're simulating, we can make our outline and document our thought process. And in the end, you also have the final plot directly in your Jupyter Notebook. So with this, we come much closer now again to the lab books that we might know from our experimental colleagues. So the idea is really that the figure that you see in a scientific publication should ideally directly be related to one of the Jupyter Notebooks that you use to develop this. And we hope to convince the community to also then publish these Jupyter Notebooks so that we can really see what are the calculations or what are the steps that you did that went into to creating this figure, and then what did you use it for. And so really abstracting this, and that's also why we make this connection to an IDE. It should be one software that you use to address all these challenges that I typically have when we work with simulation protocols and then the scientific complexity. So just to show a practical example, the first part that was important for us is just to minimize the number of imports that the user has to remember. Right? So the idea there is really we want them to be, or this to pyiron to be used very interactively. So it's really you can remember it from your fingertips and write all these lines down. We will start by only importing the project. The project can be thought of like a folder object. And then we use this project object to create our other objects. So here I create a LAMS calculation. So that's for molecular dynamics calculations. The advantage by creating this from the project object, we directly have the dependency of these objects, right? So this LAMS calculation knows that it lives in the folder named demonstration, and the calculation also has a name. The same applies for the structure. So I set here a kappa structure to my LAMS object. If I do this and then I list for interaction potentials, it would only show me potentials which are using kappa internally. I can then select one of those, and in the same way I can select how many cores do I want to use on my supercomputer, what kind of configuration I want to use there. And when I call the run function in the background, the software is doing all the steps that I showed before in the simulation lifecycle. Right? So it's storing the data, running the simulation code, and so on. So for the user, all this part is really abstracted to only focus on the scientific complexity. Right? And all the resources like my executables, my interatomic potentials, all the passes that are previously maybe stored in environment variables or where I have my given executable stored. All this is only configured once in the configuration file of the pyiron installation, but then it's not in the simulation protocol. So there's really the separation of like what's the technical information and what's the scientific part. So to illustrate this a bit more, here I'm now show the generic interface. So I iterate over different simulation codes and basically show that they all use the very same interface. And then once I have like a large set of simulations, so here it's just 2, but you can imagine several thousands, then we use a map-reduce pattern to collect this data. So we call this the pyiron table object, where basically we add functions. Some of them are already available predefined, but you can also add your own functions, as I showed here with the lambda function. These functions take a job object as an input, and then return an output which can be stored in Pandas data frame. So when I now execute this job object and get back a Pandas data frame, I see every row is one of my calculations. So that's one of my job objects inside a project. And then each column is basically one of the functions that I want to apply there. So it really behaves like a MapReduce and is a very quick way to aggregate data over a large set of calculations. So we can really iterate over interatomic potentials or simulation codes, and afterwards collect the data with this MapReduce pattern, and then maybe you analyze it with machine learning or something similar. And another development, in particular now to address the large computers, supercomputers at Los Alamos and other national labs, are what we call the worker class. So the idea there is that inside my queuing system allocation, I use the worker as like an intermediate broker, which is distributing the calculation between the different jobs. And again, this kind of complex and technical concept can be realized with pyiron in a rather simple few lines of code. So we define our worker class here, we set the number of cores to use, and then we have our for loop, which is creating more and more jobs. So in this case, 10, and they are all submitted to the worker. And then the worker is handling the distribution of these jobs within the queuing system allocation, which allows us then to scale to several hundred nodes during the execution. So the worker is really like an intermediate queue and submitting the jobs and distributing them within the allocation. So moving on, while we already have quite a huge adoption in the atomistics community, the next step for us is basically how can we extend it and can we make it more easy to also integrate other simulation codes. So here I just want to show a quick example how to integrate maybe a new simulation code or a software, any kind of software code basically inside our software framework. And we have a derived class that's a template job, and maybe quickly coming back to what I said before, right? So the interfaces. So if you import anything from pyiron, we typically recommend to import it directly. So only the parts that are available at the core level of pyiron should be used by the user, and everything else is more or less just for the internal connection between the different modules. And you see here we only need a write input and a collect output function. The write input basically takes a Python dictionary as an input, and you have to define, okay, how do I want to transform this input dictionary to the input files that my simulation code might need. And then the collect output function gets this directory as an output and returns a Python dictionary with the entries that are passed from this output. However, this is very simple to integrate new codes and really leverage the functionality even beyond the discipline of just atomistic simulations. We're very happy to be like one of the big open source projects in our community. It started at the Max Planck Institute, so we first grew inside Germany, but now also internationally we have more and more people collaborating and working with our code and giving us feedback how to grow it. So that's really like a very positive experience for us and to see how the code grows and see more and more people using it. So let me take a bit of time to now look at a couple of applications of the pyiron code. And here I brought a wide range, but I guess in the interest of time, I will just focus on the calculation of melting points. But just to highlight the others a bit, so we work on density function theory, machine learning potentials, the coupling of simulation codes, in particular for magnetic simulations, so really coupling during the runtime of the simulation codes and exchanging the information. We also use this platform for interactive workshops or teaching sessions, and more recently at Los Alamos, we even have this coupling of simulation results directly influencing the decision of experimental robots and then doing separation of nuclear fuels with them. Now coming back to the melting point, what I show here is like the workflow, how melting point would be typically calculated. And following the same coloring scheme that I used for the pyiron object before, the user inputs are marked as red, so that it would be only the interatomic potential, and as some potentials can have multiple elements, the user would also specify the element. And they can provide an initial guess for the melting point. If they don't provide a guess, we would just take the experimental melting point as an initial guess. We would then heat up the sample of the solid, fix half of it, and continue heating the other half, so that the liquid structure that we see here, and really have a solid liquid interface. If during this process, either on the first step, or the whole sample becomes liquid, or at the end of the second step, it's basically all solid again, we have an automatic feedback loop. So the code is recognizing this effect and adjusting the initial guess for the melting point to really form a solid liquid interface. And then along the z direction, so that's orthogonal to our interface, we would then compress the sample and measure a temperature over pressure curve. And again, this as we only relax in one direction, we would then take this initial the result of the temperature over pressure curve, look at the temperature at zero pressure, and take this information as an input for the next iteration until it's really converged, until really the input that we provide here is exactly the same that we get from our temperature pressure curve. To achieve this level of automation of our simulation protocol, most of the standard tools were not yet sufficient enough. Right, so here I show the detection of a typical software that common neighbor analysis, and we see that the liquid phase is correctly identified as liquid, but then within the solid region, where we see the atomistic columns here, we see that some of these atoms are still identified or cannot be clearly identified, right? So the software doesn't know if they're now solid or liquid, and only 20% can be really identified as solid. But then by combining this information with a kernel density score, we are really able to see that 46% are solid, and then the rest is correspondingly liquid. Another challenge was identifying voids. So we see in particular in the for hexagonal crystals that the liquid phase is forming these kind of voids, which again results to unphysical pressure over strain curves. And we can address this by measuring the volume around every atom and see if the maximum is going much larger than the mean. Then we maybe want to remove this data and only fit the remaining data to really have this kind of nice linear dependency. What I want to highlight with this is really there's this challenge of going from that we know practically how to calculate the melting point to we can do it in an autonomous way, right? So to really that the user doesn't have to care about it. He just starts the calculation, and at the end, he knows he gets a melting point that he can trust. And maybe one of the ways to demonstrate that it's now working automatically, we took the NIST database of interatomic potentials, picked out of this database roughly 200 potentials, and then calculated 260 melting points. And that's definitely nothing you want to do with any kind of manual intervention, right? So you really want a purely autonomous simulation protocol at this point. And what we found there is that this interatomic potentials, they really scatter quite a lot for certain elements, right? So there's easily 1,000 Kelvin temperature difference that we see here in comparison to the experimental melting point, which highlights again the importance of having these kind of tools available for a larger community to use this information already in the construction of interatomic potentials. So pyiron really enables not only the upscaling of individual calculations, but really the upscaling of these kind of complex simulation protocols and making them autonomous. And maybe to connect to our other panelists, what we then would do, we have this data set. We would then try to see if can we predict the melting temperature of an element based already on features which we can very easily calculate in our atomistic simulation. So that could be the cohesive energy, equilibrium volume, bulk modulus, derivative of the bulk modulus, or the elastic constants. And by using this information, we already find a rather high correlation. In particular, for the high temperature part that we are interested in, there's a very negligible error. With this kind of very simple approach, where we can only develop this based on having a database of melting points available at the first point. Right, so it's really this, having this existing database of target properties and then use machine learning to predict melting temperatures is only enabled by having this a tool like pyiron do this. And maybe to connect also to the other part that we discussed, right, really this process of how can we publish simulation protocols. And our favorite tool there is really working with the Conda Forge community. On the one hand, to install pyiron, and we use many of the dependencies that were already there. But then we also found that there are many tools still missing for the material science community. So over the recent years, I myself contribute more than 400 packages to the material science community. Really have them all available and make it very easy in our community to switch between different codes. Maybe try a different simulation code to see if it is able to address your topic better or more faster, or has maybe a feature that you've been looking for. And finally, we're now at the stage where many others also follow, and basically every software that's now published in the material science community is typically released on Conda Forge within the following 3 to 6 months. So that's really like makes it a lot easier for the community to exchange ideas and therefore also exchange the scientific progress by having all the software available inside one package manager. So really simplified installation for a wide range of simulation codes and tools. And with this, we really have like 4 levels of abstraction here, right? So we have this high-level user interface for a user who says, I'm only interested in this material property. I don't want to understand how it's done scientifically. We have the Jupyter notebooks that are developed in pyiron, where we say, okay, we describe the scientific process. What are the steps of simulation that we do to calculate a given quantity? We use pyiron as our technical implementation during the job management, data management, and the parsers. And then finally, we have Conda Forge as our package management to distribute all these parts. Right, so it's really the same workflow can be used by different users on different levels of experience. And as we talked about before, right, so then there's this challenge of publication and publishing software or the workflow with a scientific paper. We really try to make this easy. Right, so we provide a publication template where you can include your Conda environment. You can also include, we have examples how to include additional classes, your calculation results or parameter databases, together with your Jupyter notebook, and then you can publish it. It will render a small website using Jupyter Book, and you can execute, the users can execute it directly on my binder and interact with your data. If you want to try an example, so we have the example for the melting points that I just showed, also available on the pyiron GitHub organization. Right, so with this, we really cover the whole process, going from this idea of having a quantity that I want to measure up to the point where I publish my workflow and release it to the wider community. And maybe one more example to demonstrate how this really works. A very upcoming topic in our field is the fitting of machine learning potentials. So as I show it here, right, so the different kind of descriptors and then different kind of fitting procedures that are typically sold as like one new machine learning potential. But there's always this question remaining, if I want to take one descriptor and combine it with a different fitting engine, would this lead to better result, or would it give a different potential, maybe more performance or more precise, and so on. And so to address this question, we thought, okay, we organize a workshop, then we have a deadline and a bit of pressure to see how this implementation works. And the workshop was a great success, but then what I found even more impressive was going back and then looking, okay, how did we achieve this? How did we get there? And so I looked at my Git repository and looked at the timestamps when things happened. And we saw, okay, we created the repository in late January. It took then 1 month until all the codes were integrated in Conda and also available inside our molecular dynamics code. Afterwards, we spent 1 week to integrate the code inside the pyiron framework, another week to write the corresponding Jupyter notebooks, the examples for the workshop, and then 1 day later, we had our workshop. So this hopefully really highlights how pyiron enables this kind of rapid prototyping, and potential fitting is there only one example. So there are many different parts where we can really benefit from being able to go very quickly from getting a new idea to really implementing it and testing it. And with this, I come to my summary now. So I hope I was able to convince you that by separating the technical and the scientific complexity and providing the user with like an appealing interface in terms of like the Jupyter notebooks, in contrast to maybe the terminal that they used before, we're really able to, on the one hand, really run complex simulation protocols, but then also derive new scientific insights with these simulation protocols. And that's obviously not only just my work, but there's like a lot of people at the Max Planck Institute and also here at the Los Alamos National Lab. And I definitely thank the funding sources for the project. And I thank you for your attention.
That was fantastic. Thank you so much, Jan. I absolutely loved it and loved hearing about everything that pyiron has to offer just to simplify our lives if we're not all coding gurus, as most of us aren't. With that being said, I would like to open up our Q&A. So before we start with all of our panelists jumping in and asking questions, we do have one question from the audience from Lori Steffi, who was actually a guest panelist with us just a few months ago. And Lori was curious if you knew just off the top of your head how many pyiron users there currently are.
It is difficult to quantify, right? So
Yeah.
we have download numbers, I would say, in around the 50,000s of like the packages on Conda Forge. If I then look at the participants in the workshop, so we run 3 workshops by now. Every workshop is like 50 people using it there. But how many people are using it daily, I can't say. I guess the paper was now cited, I guess, 30 times. So at least 30 times we reach scientific output. But how many people are there who maybe used it once, maybe used it in teaching applications? So we knew. I am aware of one group in Belgium who's using it for teaching. So there are also students who have to use it. So I can't really give a number, but I would say in the hundreds of maybe active users.
Awesome. That's a great user base to say it's very strong to start with, and I'm very excited to see how many more users adopt it as this project grows even more. And it seems like it's already fairly mature, given the lengths of planning the entire life cycle that you've planned out for this. With that being said, I would love to open this up for our host panelists. If you have any questions, feel free to jump in. And James, I think I can't hear you if you are talking.
Question. I don't know if this is particularly applicable to pyiron, but it appears to me that you're using Jupyter Lab as your basically UI in order to save yourself from having to write the UI yourself. But then that means that you're being dragged along by any changes that the Jupyter core developers are making, which means that sometimes they might do something that makes your life harder. Is that really worth it over creating your own web app or your own native app that you would 100% control and you can coerce it to do whatever you want?
Yes. So I guess for us, it's even an improvement, right? So there are many people that we try to motivate for material science, in many cases already heard about machine learning and the active use of Jupyter notebooks there. So now bringing material science from which previously was most of the time done on the command line using Bash, logging into the remote cluster and so on, to the Jupyter interface really simplifies the access for them and to play around with the tools that they already know. So I guess the big challenge in our field is really getting the expertise that's there in the machine learning community and make our data accessible. Because we know that there are many interesting insights to discover, but previously there was really this gap of like, we used the terminal most of the time, and I believe that the Jupyter interface is really amazing, and we benefit quite a lot from their improvements.
Have you had to do any customization of the Jupyter Lab interface to support everything that the IDE needs, or are you basically using it as is?
There are people who customize it to adjust the layout for certain projects for parts, but for us it's mainly as is. And so all the parts, like also the visualization of atomistic structures, that's already available from the chemistry community. So yeah, we more or less use it as is.
That's really good to hear, because I know that the Jupyter ecosystem has, as soon as they ported to Jupyter Lab, I believe 3, it's when they really started focusing on kind of extensions and things like that. And so I know you probably have a lot of compatibility issues if you're trying to really manipulate and write your own extension, while also juggling all the other moving parts that this project has to contain.
So definitely handling dependencies is something that was very close to our heart, and we tried different strategies, but Conda Forge really seems to be the one that worked best for us so far.
Yeah, I was actually going to ask, do you feel that Conda in itself just kind of uniquely really enabled this project coming to fruition? If you've ever tried installing something like NumPy right through pip like 8 years ago, you'll probably know or be familiar with how challenging it could be if you didn't have all of the right compile binaries.
And I guess NumPy is still easy if it comes with pip. The issue for us was really if you tried simulation codes that are developed by people who don't have really a programming background, right? So there are many of these Fortran codes in our community, just given that maybe the community itself is not so programming heavy in most cases, right? So the documentation, I once compared the just the length of the documentation, how many pages they write, how to install their code. And there was none of the codes who had less than 10 pages. Right? So I'm happy that they write so much documentation, but that also feels a bit like there was a need for so much documentation. And so just having one line and say it's conda install and you get a first version of the code, then that's perfect. Right? So I'm well aware that there's a performance difference to compiling directly on your hardware, because conda is basically compiled to a reference architecture. But to first try the code, I think that's definitely worth it. And then if I want to do a high throughput study and have millions of calculations, I exactly know, okay, what is going to be the benefit if I compile the code on my own and it's like a factor of 2 or 3 faster? When does it make sense to spend the time and compile the code compared to just using the conda package and just spending the computing cycles rather than the precious time of the scientist figuring out how to compile the code?
So I guess I had an unrelated question. From my perspective, I don't do a lot of simulations, but I see, there's something really in common with some of the analysis workflows that we have at the light source. And this is just sort of this iterative process. So I was wondering if you have examples of people using pyiron to do sort of fitting of data using Monte Carlo processes or reconstructive sort of diffraction algorithms?
So I don't have specific examples for those, but what we did in my previous institute was like atom probe. So that's basically where it's like a needle and you pull the atoms from the tip and then you're able to reconstruct the whole sample. And there are different kind of hyperparameters to optimize for the reconstruction. So they would take the data that they get from the detector and then have similar workflows of multiple steps for possible reconstruction. And that's something that they implement in pyiron and then run these workflows. So I guess we really benefit at the point where your code needs an MPI interface and has like a longer execution time. If it's just like a short Python script, then there are other workflow managers, and I guess we mentioned a couple here. But if it's with a complex Fortran code or C++ code, that's where the part where a framework like pyiron shines to aggregate these steps and handle the submission to the computing cluster and the data storage.
Thanks.
And I'm definitely happy to collaborate on this if there's any interest to get codes integrated or have like a short benchmark. So I haven't worked with light sources so far, so I'm always curious.
Fantastic, fostering future collaborations. But I'm curious, and I would love to hear Matthew's opinion on this. Throughout your presentation, you mentioned about publishing notebooks. And I was curious from Matt, how do you think the coupling of code and results in something like a notebook, is that kind of like the future direction of publishing, or do you think that'll be something that's required for publication?
Oh, man. I have heard people tell me this, like that they want to get to a point where Jupyter notebooks are like the publication. I think it's going to be a hard sell. And the reason is just because the notebook and the publication that are associated with it do different things in a way. The notebook is an example, right? It's a tutorial, right? It can even be documentation to some degree, but you're going to find a lot of pushback in the scientific community on this. In a way, people like the style of journals, but also journals present something different, right? They present a scientific summary in a very specific way that notebooks are I just don't think notebooks are quite equipped to do. So this would be one of those times where I'd say, it's like, people ask me like, is Python better or is C++ better, right? Like, those are just the two languages I'm most familiar with. And I tell them like, I answer to them like, no, neither is better. They just have different purposes. So I think that it's the same here. You're going to see that notebooks have their purpose and publications have their purpose, and you can always link one to the other, but I don't think one's ever going to replace the other. That's my view.
So I completely agree, right? So we don't say about the notebook is replacing the publication, but there are many publications where I wonder how did they end up with this specific figure? And so to just be like, my vision for the future is I want to click on this figure and I want to see the whole code, what they did, in what, if it's now in pyiron or whatever part, how they get to this figure. What were the calculations that they set up? How did they analyze their calculations? And how was this figure created? Was there data left out and so on? Right? So, and that's really what we try to achieve with the pyiron part of publishing the notebook. On the one hand, sure, we use it to publish our methods, but also if we do just a applied paper, we use it to just say, okay, this is how we created this figure, and this figure, and this is the data that went into this figure. And you can regenerate it if you want to change the colors on the plot or maybe remove certain parts or want to zoom in into a certain section. You should be able to do this more or less interactively with the Jupyter Notebook. And that, at least in our community, reaches quite a lot of interest to just be able so open with your data that you not only say, here's a data set and figure out how to parse it, but really say, this is the notebook that I used to create my figure, and now you can zoom in and look at parts of it, how it was done, and so on.
I'll add one quick thing as well, just before I shut up. One thing I will say is that I think that this trend may go in the other direction than what people may expect. And it probably is the right direction, which is I think that for software packages, the idea of a scientific paper will hopefully become outdated. That's not to say for an app, like I'm not talking about an application. If someone used pyiron, right, and they solve a scientific problem with it, that deserves a scientific publication. But there's no reason that the software itself requires a scientific publication or should require some scientific publication. I mention this because I'm dealing with this on not only the open source, the project that's hopefully going to be open source soon, but there's another one as well. Totally different groups of physicists, mainly. And I'm getting the same pushback from all of them when I say, I'd like to release this code through JOSS, the Journal of Open Source Software. When I show them what the manuscripts look like, they recoil, right? And they're like, oh my goodness, this isn't a scientific paper. This is just an artifact. And I'm like, exactly. It's less work for me. And I'm already doing the documentation anyway, right? So I think actually the notebooks and the code docs, hopefully one day, as the community becomes more and more friendly to this, will replace an unnecessary scientific publication, right? And instead it will just be the code and will be the docs. And people will think, if I want to use this code, I'm not going to read a paper, I'm going to read the docs, because that's where the documentation should be. It shouldn't be duplicated in a static PDF that is one release. It should be a living document that moves with the code, right? Anyways, that's the last thing I'll say on the matter.
Definitely. I think that's part of kind of a field shift that we're seeing across a lot of different fields, not just physics, is kind of this shift of software is something, you can publish software tied to a DOI, specific versions and things like that. And more researchers are developing their own software to perform different tasks or perform different analyses and enable others. And right now we're kind of in this world where if you're not publishing, you're not getting grant money essentially. And so kind of we do this roundabout thing where, okay, so my software will be what gets me published and what gets me citations and then what gets me grant money so I can then do more research and continue the cycle. I'm really curious though to hear from Tanny, because a lot of this talk about notebooks and publishing just brings up a lot of the reproducibility things that we've discussed. And I was curious, Tanny, with Jan's comment about I want to be able to click on any graphic within a paper and see the code that they use to generate it, maybe in a notebook style format or any format. What are your thoughts on how sharing our code enhances reproducibility?
Well, I think that that's like a very important aspect within this reproducibility problem, although I have seen many times that, sometimes codes can be shared, but since we're running them in different instances, different clusters, especially when GPUs are involved, the whole reproducibility issue it's just very clear, like in terms of like the scientific community. But with respect to having that access to Jupyter notebooks and just sharing codes and having like a very user-friendly space for people just to go in and test the code itself and see how it relates and connect to the paper itself. I think that that is a very strong point. The more I see more papers or more software having like a little instance of like a Google Colab where people can just have easy access and just run some few things in Colab, I think ultimately it does help a lot for the scientific community to get more involved with these packages and to have like an easy access to it. But at the same time, also for them to have a better understanding of what's under the hood on these packages and have a better idea of what's going on over there, what's the code really doing in the background. Which also I think brings up a question that I was meaning to ask before. Of someone right now that is also working on software development and packages, we constantly have to also think about documentation and publications. The idea here will be, and probably my question is like, is there any advice that I could get or the scientific community could get when it comes to grading documentation? Like, how do I know that my documentation is good and where do I stop?
Yeah, so I guess I can answer it for our package. Similar, like we divide the interface to say there's a certain part that we want the user to use and work with these objects and interact with them and build their simulation protocols. That's the part that we try to document quite well and also have quite a series of examples there. Then the documentation on the internal workings of the library, we try to improve there, but maybe there it's more difficult to motivate the people, and there's maybe too much change or it's too fluid. Still, the documentation there is not so consistent at the moment.
Perfect. Thank you so much, Jan. And I think on that note, we'll go ahead and wrap up today's exchange. I would like to extend a huge thank you to all of our host panelists and our guest panelist, Jan, today for what I thought was a fantastic exchange with some great discussion. For next month, we are joined by Max Grover and Zach Sherman from the PyArt community. They will be discussing PyArt and how it can enhance the lives of researchers, much like Jan's project and pyiron did today. For a recording of today's exchange, keep an eye on our Meetup website. That's meetup.doepy.org. We will be posting an edited version of today's exchange up there shortly. Additionally, when you're on our website, if you want to stay up to date with all of our invitations and everything that we do with these exchanges, please sign up for our mailing list as well. With all of that being said, I think we can go ahead and adjourn for today, and I will see you all next month. Thanks, everybody.